Hello and welcome back to Mr. Linford's math course. This video is going to continue our talk about the application of distance, rate, time problems, and in particular we're going to look at some more car problems where cars are traveling towards and away from each other, and we're going to see the relationship between their distances and that of rate and time. Now in this problem, the WTMC staff has lucked out. Someone has brought in donuts for the whole staff. Awesome! Unfortunately, there's not enough for everyone. Mrs. Zimmerman texts Mr. Linford and Mr. Long that they better hurry into work since there's only one donut left. Well, Mr. L and Mr. L hop into their fastest cars and speed off to WTMC. Now, Mr. Linford decides to drive his Bugatti Veyron 16 miles west, while Mr. Long takes his Aston Martin 177 east, approximately 14 miles. Now, if the Aston Martin can travel 220 miles per hour at max speed, and the Bugatti can go 268 miles per hour max, which instructor will get to the office first? So let's see what we have going on here. First off, we have Mr. Long in the Aston Martin. And the Aston Martin, let's write down some of its specs here. We know that the rate of speed for the Aston Martin at max is 220 miles per hour. And we know that Mr. Long has to travel a distance of 14 miles. Now, Mr. Linford is in the much faster Bugatti, and my rate of speed is 268 miles per hour. And I have to travel a bit farther at 16 miles. So the question is who is going to get to work first? Mr. Linford or Mr. Long? So what do we need to find here? We know their distances, right? We know how far each of us has to travel, and we know how fast we're going. And we're going to assume that Mr. Long and myself left our houses at the exact same point in time. Right? We're assuming that Mrs. Zimmerman texted us both and we left at the exact same point in time, right? Neither one of us had a head start. So what we're trying to do is figure out who took the longest amount of time or who took the shortest amount of time. Whoever got to work first obviously got there quicker. So we need to find the times for each person. Who drove longer and who drove quicker. So let's see if we can set this problem up and figure out what is going on here. Now in this problem we had the two situations. Let's talk about the distance for Linford. Here was the setup to that equation. 16 miles is equal to 268 miles per hour times some time for Linford. And then for Long, this was Long's equation, we had 14 miles. That's the distance Long traveled. And he went 220 miles per hour that entire time, but you don't know what the time is. Okay, so we have the time for Long and the time for Linford. Now, how do we find these unknown quantities? Well, it's very simple. Hopefully you're saying divide both sides. That's how we are going to isolate the variables. So divide both sides by these quantities, and let's see what we're left with for time. Now, if you were to check for Linford, let's see, the 16 miles divided by 268 miles per hour, that is 0.0597, let's say, is equal to time. So this is, by the way, this is in hours, remember. So roughly 0.06 of an hour. So that's 6/100ths of an hour it took me to get into work. Now for Mr. Long, who had to drive a shorter distance but had a slower car, he got to work in 0.064 hours. That was his time. So let's compare. Who got to work quicker? Well, it took me less time to get into work. Now, I drove the shorter amount of time. In this setup here, you will notice that really we're not comparing the distances in this problem. In this problem, we said that the main thing we need to find are the times for both. So in this setup, this is a fairly easier, more straightforward problem. We don't need to set up the actual distances and set them equal to each other because we're asking for the specific times for each situation. And we took what information was given and we set up the individual equations. So this is the idea that we really need to hit home with when we have to go and read the problem and identify what we need to find. Make sure as you read through the problems that you're given for homework and practice, make sure you're understanding what is it that I need to find and how do I find that information. Maybe it could be as simple as this setup. So in this problem, we can quickly see that Mr. Linford is victorious and he gets to work in time to get the last donut. Unfortunately, for both myself and Mr. Long, Mr. Zemper also heard about the donut, and he decided to drive his Koenigsegg Agera R Series east to the office and beat both of us. So if Mr. Zemper drove from his house to WTMC in 0.04 hours, that's 4/100ths of an hour, and then he drove back to his house at the end of the day in 0.06 hours at 95 miles per hour slower, how fast did his car travel to get to work? So let's think about this problem. We have Mr. Zemper driving from his house to WTMC. So on the first trip, from the house to WTMC, Mr. Zemper drove 0.04 hours, so 4/100ths of an hour. When he went back, he drove a bit slower. He drove 0.06 hours. He drove 6/100ths of an hour, a little more time. Okay. Now, I don't have any information about the distance from Mr. Zemper's house to TMC, but I know that his rate of speed is related in both instances. I'm not told the rate of speed, but we do have this setup that it's 95 miles per hour slower going home than he was rushing into work. So what I'd like you to do is pause this video, see if you can set up how to represent the rate of speed for Mr. Zemper going to WTMC and going back to his house. So when I look at this problem and I see that we're trying to find the speed of the car going to work, we're trying to find this rate of speed right here, I know automatically I want to make that the variable x. I want to make that the thing I have to find. So how do I represent the rate of speed going back to his house from work? Well, we know that it's the rate of speed he went going to work, but 95 miles per hour slower than that. So however fast it took him in the morning to get to work, he went 95 miles per hour slower. So we're going to say x minus 95. And here we have our setup. We have our we have our rates and times for each trip. Now in this case, how can we set up the equations for distance? How can we set up and solve for the x variables here? We know that these rates and times explain distance 1, and these rates and times explain distance 2, the distance of his trip back to his house. So how can we work with these two quantities here? Well, hopefully you're saying that this problem really is one where the distances are equal to each other. We can see that Mr. Zemper has made the same trip twice. He's gone from his house to work and work back to his house. So, in this situation, we're going to set the distances equal to each other. And if the distances are equal to each other, then we can set their rates and times equal to each other. So I'm going to set 0.04 times x equal to 0.06 times x minus 95. And this is saying that the distances are equal to each other, so now we have something in terms of x. Let's go ahead and solve this. I'm going to distribute the 0.06 through. So we get 0.04x is equal to 0.06x, and then 0.06 times the 95, we're going to subtract 5.7. Now let's get the x by itself on one side. So I'm going to subtract 0.06x. And that is negative 0.02x is equal to negative 5.7. And if I were to divide that on both sides, we would get x is equal to 285. So x is equal to 285, and remember, what did x represent? That was the speed Mr. Zemper drove to WTMC. So Mr. Zemper beat both Mr. Long and myself by driving to work. He covered his whole distance from his house to TMC in 0.04 hours, so 400ths of an hour, by driving 285 miles per hour. All right, Zemper, you win this time. All right, well, if you have any questions about this problem and the different components to it, how it was solved, feel free to go ahead and send me an email. Let me know if there's any questions you had in the video or any comments. My email is klinford, that's KLINFORD, @wccnet.edu. And until next time, take care.